CellPaint is an interactive application that enables non-expert users to create models that integrate biological data into illustrations of cellular environments. It uses the approach of popular digital painting software, including palettes, brushes, and other tools that enable rapid construction of static and animated illustrations. Different palettes are presented for different biological compartments. Here we select a palette for HIV and choose a membrane brush to draw the shape of the virion as it exists in blood plasma. Next, we move to the cell palette and again choose a membrane brush to define a portion of the immune system cell that is the target of the virus. We have defined 3 distinct compartments now: the virus, the cell, and the blood plasma. We return to the HIV palette to insert 2 types of viral membrane proteins: the envelope spikes that aid in cell entry and a structural matrix protein. We can decide how many and where each protein is placed. Notice that the membrane proteins are constrained to lie in the membrane and cannot be placed inside or outside any compartment. We choose another HIV protein, capsid, and create a new compartment inside the virion, the capsid core particle. Next, we return to the cellular palette to populate the cell membrane. Here we place cellular receptors and co-receptors that the HIV virion uses to enter the human cell. To the interior of the cell, we add soluble proteins like these ribosome assemblies, the large protein manufacturing machines, and a fibrous ingredient such as messenger RNA, the instructions for protein building machinery. Another fibrous cellular structure is made of actin proteins. Actin fiber can interact with cell membrane to give it shape and also to produce cell mobility. With fibrous or membrane elements, the CellPaint brush enables the drawing of continuous lines of any number of elements of the given type. We can then fill out the cellular interior with a number of other soluble proteins, such as enzymes and signaling proteins, in other molecular machines. Each molecule is represented by a sprite based on known atomic structure, and their relative sizes reflect the actual molecular size. Now we go back to the HIV palette to populate the virus interior. First, we place the viral enzymes and the viral RNA into the capsid core particle, which will deliver the processed viral genome to the cell nucleus. Then we fill the volume outside the core with other viral proteins, including restriction factors that aid in viral infectivity and some proteins carried from the previous host cell. Finally, we select the blood plasma palette to place molecules in the fluid surrounding the virus and the immune cell. We first add serum albumin, the most prevalent protein ingredient in blood. We next add immunoglobulins, antibody defense molecules that can recognize viruses, and then ferritin, a protein that transports and stores iron in the blood. We track the number of each type of molecule that we add so that we can target the known concentrations of each ingredient. Each molecule occupies its own space as specified by their attached circular colliders and moves out of the way of others. We can insert random motion into the scene by raising the temperature by way of the thermometer slider. This not only helps to randomize the distributions of molecules, it also can serve to simulate diffusive motion in the scene. As we zoom in, we can see that the sprites exist in 3 layers, with color value decreasing front to back to give a sense of depth.